Hey everyone, this is Derek, and in this video we're going to look at kind of the first round of applications involving exponentials. We're going to build on this idea pretty much through the end of the course. So we have a couple of forms. We've seen ones that kind of look like this when we're doing the graphing. This is actually the exact same thing. Let me kind of go through what all the pieces are, but it's two forms of basically the exact same deal. So A in both cases is the initial value. I did one in the last video where it was like f of x, it might have been a y, equals 2 to the x. When x was 0, 2 to the 0 made 1, and then 1 times 3 makes 3. So what that's giving us is our y-intercept. It's also giving us our initial value. And so that's what this number in front is going to be. So if I have an initial population at time equals 0, that's where we're starting from because it's the y-intercept. B is what's called the growth factor. Growth can be positive, and then it could also be negative, right? It could be decay as well. And we have this way of writing it over here where it's B equals R plus 1. So these two pieces are interchangeable. What's nice is if the directions of the problem say something is increasing by 17% per year, this is 0.17 plus 1, and that's your 117%. So that's what this is showing. It's just giving you a way to kind of break up that B into two pieces, the rate and then the original value. And then R, of course, is the rate in decimal. So let me show you how to apply that to something with some words. We have a population of 19,000 organisms, and it's going to grow by 10.1% per year. Suppose P represents population, T is number of years of growth. Find an exponential model of this form. Okay, so capital P is going to equal A. So A is our initial value, right? So that's the 19,000. And then B, it's going to grow by this percent per year. So we're saying 1 plus point, and then we have to move our decimal two places because we're right here, we're in percent. So we're going to change over to decimal. Oops, but we're going to write it right. There we go. Sorry about that. To the T, and then writing that a little bit better would be 1.101, which is probably what I should have just written in the first place, and then P. And then that's all that question's asking for. It's just asking to set up the equation. Okay, so for this one, the fox population in a certain region has a growth rate of 4% per year. It's estimated that the population in year 2000 was that much. So that's going to be our rate, 0.04, and then this is our initial population, which I think we've been calling A. I'm used to calling it P naught, which is the initial. Find a function that models population 2 years after 2000. So we're going to let, basically we're letting 2000, that's going to be T equals 0. And then, so 2001 will be 1, 2, 3, etc. So our equation will look like population is going to equal the 15,300 that we're starting with. And then that's going to be times 1.04, so that's our 1 plus our rate, and then raised to the telling us our variable is T. And then use the function from part A to estimate the fox population in year 2008. Answer should be an integer, so what they're saying is there's no partial foxes, so we want to round to the nearest fox. So P equals 1530. And then we're just going to put in a 8 there, right? Because this is the same thing as T is 8. And then when I put that in the calculator and rounded, I got 20,939. Okay, for this one, a vehicle purchased for $25,000 depreciates at a constant rate of 4%. Determine the approximate value of the vehicle 13 years after purchase, round to the nearest whole dollar. Okay, so it's the same formula. This time instead of P, I'm going to call it A for just amount. And our starting amount was at $25,000. And this time, and I'm used to it being 1 plus or minus rate. I think this book has the rate first. I keep writing backwards, but same thing. So 1, but this time our rate's negative because it's depreciating, it's going down. So instead of saying plus, I'm going to say minus 0.04. And then that's going to be to the 13,2500. And then what this is it's giving you 0.96, which means it's going to be, if something is depreciating by 4%, that means it's 96% of what it used to be worth, right? So if it's dropped 4%, it's still worth 96%. And then we're going to do that 13 times. And when we do that 13 times, then our vehicle is worth $14,705 to the nearest dollar.